Thanks for inviting me to this parity violation from home conference. My name is Matteo Galaverni. I'm now at the Specula Vaticana, the Vatican Observatory in Castel Gandolfo near Rome, and I'm also associated with INAF in Bologna, and this work is the result of a collaboration with Fabio Finelli and Daniela Paoletti. I will speak of the importance of redshift evolution for cosmic birefringence. I will start with a quick summary on cosmic birefringence, the current constraints, and later I will focus on the importance of time redshift evolution of the pseudoscalar field. And I will conclude showing the constraint that can be put for early dark energy, and dark matter models. When photon propagates in a time-dependent background of pseudoscalar particles, we have this Lagrangian, we have the standard electromagnetic term, we have the potential for the pseudoscalar field, and you have the usual coupling term between pseudoscalars and photons. When photons propagate in a time-dependent background, the plane of linear polarization is rotated independently by frequency. You see in this equation, for a single photon, the rotation angle alpha is proportional to the difference between the pseudoscalar field at emission and detection. This was already studied in the early 90s by Carol Field and Jakiv, and later by Harari and Sikiv. We all know that CMB is partially linearly polarized through Thomson scattering, and here you can see the Planck 2018 map for linear polarization. CMB linear polarization is described using E modes and B modes. Note that E modes here are parity even under mirror symmetry, but during propagation, if cosmic birefringence rotates linear polarization, you'd end up with this pattern, which is not anymore parity even, but it's parity odd. So a certain degree of B mode parity odd polarization is produced due to cosmic birefringence. Here you see the birefringence-induced B modes for a rotation of 1 degree, 0.5 degree, 0.1 degrees. And there is a simple analytical expression connecting the power spectra at recombination with the B modes power spectrum observed today. Similar expressions are possible also for the other power spectra, and note that in this case also TB and EB parity odd power spectra are generated, always assuming a redshift independent rotation. Several CMB polarization experiments provided constraints on isotropic cosmic birefringence, and there was quite a big improvement starting from the boomerang constraints up to today. This point corresponds to the 2016 constraint by the Planck collaboration. Recently, there were also several claims of a non-zero detections of an isotropic birefringence. In order to consider the effects of a time-dependent rotation angle, we consider the Boltzmann equation and the additional term due to the rotation of linear polarization. You see there is an additional term proportional to the derivative respect to conformal time of the rotation angle. Following the standard line-of-sight strategy, we obtain this expression for the source terms, and there are two additional terms for the E modes and for the B modes related to the rotation angle. You see here you should insert the behavior along in time of the rotation angle from last scattering to today. In the integral also appears the visibility functions, the probability of CMB photons to last scatter on electrons you see that it is not a constant function in time or in redshift, but it has its maximum at recombination and another peak at reionization. Here you see three different behaviors in green of the rotation angle from last scattering to today. They are only phenomenological behaviors. Here the rotation angle starts at 0 and ends up in 0 at today. So following the standard approximation which neglect the evolution of the rotation angle in time, there should be no effect on the power spectra. But if we take into account the time dependence of the effect, as I showed you in the previous slide, you see that also in these cases there are effects on the power spectra. Here you see the B modes power spectra. And if the rotation angle does not oscillate too quickly, there are still effects on the power spectra. Also, if the value of the angle at recombination and today is the same. More interestingly, we can consider a pseudoscalar field acting as early dark energy. In this case, the field starts to oscillate, and at recombination it is already oscillating with this behavior of the background. And as you can see in this slide, the redshift dependence of the pseudoscalar field induces a non-trivial multipole dependence of the cosmological birefringence effect in the CMB power spectra. For example, here for B modes, you see that the power spectrum obtained with the modified version of CAMB, taking into account the time dependence of the rotation angle, is different from the red lines, which simply takes into account the difference between the rotation angle at last scattering today without taking into account the time dependence. There is a clear difference in the multipole dependence. With the modified Boltzmann code, we can also estimate the modifications for E modes and TE modes, and also estimate the effect for TB and EB. And we estimate that in order to have an isotropic birefringence of the order of 0.35 degrees, this is the value of the coupling constant that should be present in order to have this effect. In order to estimate the capability for future missions, we considered a light-bear-like mission, and due to the parity-violating nature of the interactions that generates also the parity-odd correlators, we consider the full theoretical covariance matrix in our estimates. The noise power spectra are obtained by considering an inverse variance-weighted sum of the noise sensitivity convolved with a Gaussian beam window function from each frequency channel as listed here in this table. Then we considered this expression for the effective chi-square, where also the parity-odd correlators TB and AB are considered. Always in the early dark energy case, using Cosmo MC, we considered some explanatory runs with not only the 6 standard cosmological parameters, but also the time-dependent birefringence and a time-independent rotation of the spectra, a miscalibration. And for two cases, optimistic and pessimistic. And as you can see in the plot, there is still a correlation between the miscalibration angle and the coupling constant, but the degeneracy, as would be neglected the redshift dependence, is broken, is reduced. Here you can see a different profile for the pseudoscalar field, acting in this case as dark energy with this potential. You see that the field here in redshift is constant and starts to move only quite recently at very low Z. And these are the effects on the BB power spectrum of this kind of dark energy birefringence. In this case, since the rotation happens quite at low redshift, the shape of the power spectrum is quite similar to the constant rotation angle approximation. And also for this dark energy case, we estimated the order of magnitude of the coupling constant that is needed in order to produce an isotropic birefringence of this order of magnitude, 0.35 degrees, and the bound that you can put on the coupling constant with a light-bear-like mission. Last case we considered is that of a pseudoscalar field acting as dark matter. In this case, we have this axion-like particle potential, and this is the evolution of the pseudoscalar field from last scattering to today. And you see the fields already oscillates very quickly at last scattering. Here you see in green the BB power spectra induced by birefringence with this value of the coupling constant, and on this side you see the exclusion plot. A first version of the exclusion plot we realized in 2009. Here you have the mass of the pseudoscalar particle, and here you have the coupling constant, and this red region is the region that is possible to exclude with birefringence. And this is an updated version of the previous plot. You see here in blue the region that can be tested with birefringence, and this blue line corresponds to the value of the coupling constant as a function of mass that is needed if we want an axion-like particle acting as a matter to induce a rotation of this order of magnitude, 0.35 degrees. This is a quick summary of this talk. I try to stress the importance of redshift time evolution of the birefringence angle and try to show the important effect on the spectra. So it's not only important the amount of rotation, total rotation, but also when the rotation occurs. And this induces different multiple dependence on the power spectra. And we try to study these effects for some phenomenological models and also for theoretical motivated models like for early dark energy, and dark matter. And also try to estimate the order of magnitude of the constraints that can be obtained looking at the cosmic birefringence. For the future, we are also thinking to consider anisotropic effects, but we are still working on this. Thanks for your attention, and I'm happy to answer to questions, discussions, and thanks again for the invitation.